Hello.
Yes, sir.
Good day.
Uh, Good morning, sir.
Good afternoon, sir.
Good afternoon.
So may we start, sir?
Yeah.
So a very good afternoon to all the participants of this 1 week online faculty development program on new approaches in geotechnical earthquake engineering. We are at the third session of first day, and we have with us Dr. Wesley Golubev, sir. We are highly privileged and honored by your presence, sir, and we thank you for taking time out of your busy schedule and enlightening us over the burning issues. So, Golubev sir is an associate professor at Moscow Institute of Physics and Technology, Russia. He is also working as a senior researcher at the Laboratory of Applied Numerical Geophysics. He is a doctorate and graduate and postgraduate in applied mathematics, computer science from Moscow Institute of Physics and Technology, Russia. He has been awarded as the Russian Academy of Sciences Medal to Young Scientists in 2018 and as Research Excellence Award Russia by Elsevier in 2021. His area of concentration is the development of mathematical models, numerical model methods, and applied computer programs for hyperbolic problems, seismic survey process, and seismic resistance estimations. We are indeed fortunate to have an interaction with you, sir. Thank you so much for being present with us today. I request Golubev sir to please take over the session, sir.
Thank you very much. It is. I'm. It is a great chance for me to present our latest research and development results in the area of numerical simulation of complex mechanical dynamic problems. Thank you for this chance. Thank you very much. And I will present shortly my laboratory, my university, and then we'll start the presentation. First of all, I would like to say that I'm a part of Moscow Institute of Physics and Technology. I have here a full-time position as a numerical simulation department. As a, it is a at least at my I think that I will not be wrong if I said that it is one of the famous Russian university. Nowadays, we have a lot of very talented students here, and we provide next generation for Russian Academy of Science. A lot of our students decide to go abroad to study at top-ranked university like MIT, Oxford, Harvard. So a lot of my colleagues work in some international collaboration with some other countries, with some other university, and according to the direction headed by our rector, we try to extend this collaboration with other countries, with other university, and I hope that we will work together under very interesting and promising seismic estimation resistance problems, seismic ground estimation and detection and prevention. So I hope that we will extend our collaboration. And I'm also a part of the Laboratory of Applied Numerical Geophysics. Our research is connected mainly with the development of modern method of seismic wave simulation in complex geological medium. One of the goals is to simulate the process of seismic survey for oil and gas deposits, for ore deposits, and we have some good expertise in this direction. Also, we have the sub-team inside our group connected with electromagnetic simulation, marine seismic survey simulation, and also we are developing a joint algorithm for inversion of electromagnetic and acoustic or elastic, seismic data. The international head or co-founder of our laboratory is Professor Danov. He is a full professor at the University of Utah, USA. So we try to be on the bleeding edge of the science. So I will try to discuss today only one part of large out scientific direction connected with seismic wave simulation and one specific numerical method, grid characteristic method, that was extended significantly by the Russian academician Professor Holodov, and also my scientific advisor, the correspondence member of Russian Academy of Science, Professor Igor Petrov. So now I want to share my screen, if it's possible to start the presentation.
You can share your screens.
Right now, no, you have to switch on some function at your side, I think.
Okay.
Yes, now it's available. I started. Please say when you will see it.
Yes, sir, it is visible now.
So the title of my presentation today is Dynamic Problems in Spatially Heterogeneous Media and the Grid Critique Method as a way to solve their mathematical and physical problems numerically. So let's start. First of all, let's say a couple of words about the main direction of my talk. Everything that I will show today here will be closely connected with the hyperbolic problems. In fact, mostly with linear hyperbolic problems. And as it is quite obvious that hyperbolicity means wave behavior, behavior of media. There are numerous applications of hyperbolic theory, hyperbolic problems. First of all, in the order of the connection with my scientific research, the first one is the seismic survey process simulation as direct problems when we know the media, we know the spatial pattern of elastic parameters, spatial distribution, and we want to simulate how seismic wave will propagate in heterogeneous media. We want to simulate all diffracted waves, all surface waves, volumetric waves, etc., etc. And also the inverse problems. There are two major problems. First of all, seismic inversion, when we want to analyze somehow data on the day surface and want to estimate the spatial distribution of elastic parameters or density inside our subsurface media, subsurface space. And the second one is a migration problem, when we want to track only the position of highly contrasted layers, maybe some point diffractors, positions, etc. The second major direction is the seismic activity simulation, how to simulate the earthquakes, how to simulate tsunami, how to simulate elastic or viscoelastic or viscoplasticity and elastic waves propagated in the far away from the hypocenter, and its interaction with the structures like houses or something like this. The third one is a non-destruction control as an application for novel composite materials design. How to test its internal destruction that is invisible by other methods. And the last one is the ultrasound diagnostic of diseases, modern method of ultrasound diagnosis, non-acoustic methods, etc., etc. Let's start with the isotropic case when we have some media and we want to describe the behavior, the dynamic behavior of this media by introducing elastic parameters like density and lambda and mu as the Lamé parameters, as a compressibility modulus, and we want to describe our media as a continuum in the continuum approach when we have velocity vector and stress tensor as a function that depends on the time, and also the coordinate vector r that contains 3 coordinates x, y, and z. We can write the second Newton law here in the tensor form, and we can also extend it by the relationship between stress and displacement or strain tensor. So this system is hyperbolic. We have to set appropriate amount of boundary conditions and initial condition too. And if we have an isotropic case, this system will give us 3 different type of waves. In fact, single pressure wave and 2 different shear waves. Our goal will be to describe the behavior of heterogeneous media. Here I will show you a short video when we have some inclusions and we have also some cracks inside our medium. We will construct triangle meshes and solve this system by the hyperbolic method, by the grid characteristic method numerically. So we have current time layer. This method is explicit a long time. We have the initial condition, we have current time layer, and we will calculate all of values at the next time value. Repeating this procedure in the loop appropriately, we will solve eventually our problem, dynamic problem, and then we can show the results as a video or a set of wave patterns of a set of spatial images. I will run it. So here you can see triangulated area. We think that inside this inclusion we have different material. For example, methane. It is this example is connected with oil and gas deposit seismic exploration, seismic survey process. Here we have fluid saturated cracks, but fractures, but we will not generate a mesh inside this crack because it will significantly decrease the speed of simulation. We will apply the other approach. We provided here the specific contact condition here to fulfill the discontinuity condition of stress tensor, of vector of velocity, some components of this vector. We can introduce here some friction law. In the color scale, the modulus of velocity is presented. You can see here small arrows. This is the direction of velocity, and the yellow one or white one is the maximum of the modulus of velocity. So this is a P wave propagated from the day surface, and we have a lot of inclusions here, and we can see the generation of the seismic response here. This response contains a lot of information about the structure of this inclusion, the spatial structure of this inclusion, about the parameters of these inclusions, and we have to process this data at the day surface register to estimate somehow this structure. So let's speak a little bit about possibility of extending this paradigm, this method. In the general case, we deal with the isotropic medium when we have the relationship between the stress tensor and the strain tensor, and this contains only two different parameters, lambda and mu, as shown here, lambda and mu, and we don't have any dissipation. If we have some viscosity, we can deal with the same relationship, but introduce the function. In fact, this is the exponential decay of our stress tensor components with a characteristic time tau 0. It will lead in the dissipation of energy. We can extend our approach by some modern and very well tested elastoplastic materials like Brandt rays or Tsai-Wu criteria. So in fact, if we deal with hyperbolic medium, we can apply successfully grid characteristic method on different computational grids, and also we can solve a non-homogeneous equation. If we have some right part, we can apply some method of Range-Cook to preserve the same approximation and convergency order and stability criterion. The distinctive feature of the hyperbolic equation is that they may have discontinuous solution even in the case when we have continuous source, like in seismic survey. We can have the contact of different materials like clays and sandstones, and at the interface we have the discontinuity of coefficients inside our equation, so we will obtain the discontinuity in our solution. But initially, the grid characteristic method was generated or was developed for the dynamic problems connected with high-speed propagation of discontinuities like the shock waves. And in our group, in the frame of the work of my scientific advisor, it was successfully adopted to the elastic elastic equations, elasticity equations. Let's deal with the simplest hyperbolic 1D equation. This is a linear transport equation with a constant coefficient lambda. And if it is positive, we can easily obtain the solution. Let's deal with the initial condition. And if we know the solution in the current time step at some nodes, and we want to calculate the solution at the same node in the next time layer after the tau seconds, we can go back along this characteristic curve. The equation of this line you can see here, because and bring the value from this point, and the value at this point will be the same, totally the same at the next time layer. Why? Because any function that depends on this set of x and t will be the solution of this equation. This is the analytical solution. Any function that depends on x minus lambda t. So if we have here some initial data, we can solve. We have to solve at the current time layer the problem of 1D interpolation. We can introduce some spatial stencil like this one point and that one point, and using these 2 points, we can reproduce a single linear function with 2 fixed coefficients. So the order of this approximation procedure will be the first. And the major fact is that the convergence order of and approximation order of our final numerical method will be the same as the order of approximation. So if we want to extend the approximation order, we can introduce one more point and construct the second order, the method with the second order approximation, the third order, etc., etc. All of you, I think, know that the domain of the dependency for hyperbolic medium is the cone. So for this particular case, the data propagates from left to right. So we have to rely only on this data from the left point of this node. But if we will analyze the numerical schemes produced by this approach, we will see that most of these schemes is unstable, unconditional unstable. So we have to add more points from the right part. It is not very physical, but in fact, it allows us to stabilize the method. And we can also deal with a set of schemes for this 1D equation with coefficients that depends on the tau and h, the spatial and time steps. And these methods can include different stencils, not only at the current time layer, but also at the next time layer. In this case, we will obtain implicit schemes. But in our work, we deal mostly with explicit schemes because the mathematical problem is large, and we have to utilize modern MPI and OpenMP technology to run on supercomputers to solve our problem in fixed time. So if we will write the formula for all of these schemes, we can easily derive a first order condition, this condition for the first order schemes and for the schemes with the higher order using the Taylor expansion. And one of the things is that it is very well known that it is impossible to construct the monotonic scheme for hyperbolic problems with the approximation order larger than 1. And to deal with it, there are a lot of different approaches. A lot of monotony criteria were introduced, like Friedrichs for only positive values of coefficients, Harton like TVD approach, Van Leer or grid characteristic method, equalizer. But in general, we use the third order schemes. Why? Because we can't bring a lot of numerical cells, special cells, limited with our HPC powers, and we want to provide a good resolution of our waves. To deal with monotonicity problem, we use the analysis in the domain of these unknown coefficients, and according to some analytical analysis, we can provide the third order scheme that is that is closest to the domain of monotonic schemes. The title of the scheme is Rusanov. It is very well known scientist, and this scheme is very well known. So we used Rusanov schemes in our software. Here you can see again the illustration, but for 3D case, in fact, what we do, first of all, we introduce the method of spatial splitting. It means that we will solve a set of 1D problems using different matrices. Matrices were derived based on the neglecting a couple of terms inside our initial equation. If we have 1D problem, we can calculate analytically omega matrix that contains eigenvectors and lambda diagonal matrix that contains eigenvalues. And dealing with this equation, multiplying from the left part on the omega and introducing some other unknown variable v, we can derive a set of 1D equations for V components and V components called Riemann invariants. So we will solve each equation, transport equation for each invariant, and then multiply the solution on the inverse matrix of the omega to reproduce to calculate the vector of unknown physical parameters on the next time layer. Unfortunately, this approach is limited. The splitting introduced some error along time axis, and the final approximation order depends, in fact, on the splitting technique. One of my master students developed one interesting approach based on the multi-step splitting technique when we have S different iterations and we have different fractional time steps. So to preserve the third order provided for us using by our usage of the Rosanov scheme for 1D problem, we have to do three, in fact, iteration with these parameters. And it should be noticed that we have here the negative argument. So in fact, one of the last step will be the inverse step along time. But because we did hyperbolic problems, it is not a problem for us. So we formally go along the other characteristic curve. So everything is fine. And here you can see the possibility of reproducing of analytical solution for 2D case when we have acoustic problem in homogeneous medium. We have some direction and we initialized p wave along the direction, and we know, of course, the analytical solution. So the analytical solution is depicted with the black line, and green one is the usage of the Rosanov scheme with the third order splitting scheme, and the red one is the fourth order splitting joined with the SimForce scheme on the white stencil, special stencil, and you can see that according to L1 and Lfinity, we can achieve the fourth order of convergence. But of course, it significantly increase the computational time, at least 3 times or 4 times more. But the demand of the random access memory of this software is the same. It is not necessary to do something more. Simply multiply by 3 or by 4 the computation time of our trivial splitting technique. And of course, we have here some time steps less than 1. Some of these coefficients is less than 1. Some of this coefficient is higher than 1. So we also restrict, according to the current stability condition, we somehow restrict dt time step of our numerical algorithm. What we can do if we have discontinuity in our model, we can't use directly the interpolation procedure, because what if we try to use the some polynomial function? Obviously, all of the derivative of this polynomial is continuous. That's why we can't reproduce some discontinuity of the first derivative or second derivative of our solution, but we can use the compact scheme when we have only a couple of nodes, like one here at the border or at the contact border and one at the left body or at the right body. In this case, we can think about this subdomain as a separate subproblem, and we can introduce the discontinuity of the initial vector at this contact boundary. This is a natural condition, but also we can differentiate our initial equation at the left part of this domain, and also obtain more discontinuity conditions that will contain not only the derivative of our solution, but also the parameters of our materials. That's why we can construct the second order schemes for this case when we have some discontinuity at nodes and not inside the cell. Here you can see the results of the usage. The first order current taxonomy scheme. We can see the analytical solution, and we can see huge dissipation of the first order scheme. It's natural. We can use the third order of the accuracy schemes, cubic interpolated profile scheme, but the scheme contains or produces some non-monotonic behavior of the solution, and we can use different monotonization procedure like BIS1 or BIS2 to preserve the precision of the third order scheme and also remove this oscillation. In fact, this approach based on the hybridization of the spatial stencil. If we have 2D schemes, we have 2D problem, it is a little bit complex to apply this approach straight for in the natural manner, but we can solve the transport equation for the orthogonal component of the derivative with some scheme like the first order scheme, and this will give us the third order of the accuracy of the final scheme. Here I put the test of the approximation order, the representation of the trivial case when we have initial condition, we have first order scheme, and we have a third order scheme with the monotonization procedure, and non-monotonic solution obtained by the third order scheme without the monotonization procedure. But the real example is here. This is the model of the ore deposit, and we applied our second order scheme honestly to this simulation of acoustic in this domain, quite complex domain, and you can see the comparison of the traditional scheme applied at the left and our novel scheme applied, and you can see that the width of the initial wave was reproduced precisely, and also we can detect a lot of different scattered waves here with like surface waves propagated on the surface in this media in this layer. So this approach, first of all, I have to say that we at least have to increase memory consumption of our program. We have to provide more HPC resources, but we can simulate quite precisely, a realistic model provided for us by other groups. When I told about the different logical relationship, I told that it is quite natural to introduce different viscoelastic models or viscoplastic models. And here I put the result obtained by my second master student. We have to simulate the ice island model in the sea. We have here artificially created ice island, and we have here some ice around this, natural ice around this island. We have a water, we have a multi-layered subsurface geological massive, and we have here the methane reservoir, and we want to simulate the full wave, to solve full wave problem here when we have the seismic source on the surface of this island, and we have to detect seismic responses from this inclusion. So we successfully solved this problem and obtained detectable signal-to-noise ratio. Let's say a couple of words about the research software. Our group is headed by my colleague, Nikolai Khokhlov. He is also part of MIPT department, one of the departments of MIPT. And here I put some key features of our software. We can simulate precisely seismic wave in elastic media, taking into account cavities, layers, fractures with different feeders. We can use discrete and continual models of destruction based on some plasticity criterion, based on some periodic models. And of course, our software was is in-house code developed on C++ and with micro optimizations for modern architectures, and also we intensively used MPI and OpenMP technology, and nowadays we also have a cluster of GPU, mostly CUDA. So multi-GPU approach is very helpful for 2D problems nowadays. We support a wide range of meshes. Unstructured meshes like curvilinear or like triangle or tetrahedral in 3D, and also structured meshes to speed up the simulation. This is a rectangle mesh, a curvilinear mesh, and a hexahedral mesh. Here I will show you the mesh for taking into account the topography of the day surface. We can also take into account the curvilinear boundaries between different geological layers explicitly. So here I put the scalability tests up to 16,000, of course. At Edinburgh, they have the Hector system, and they give us enough time to test our software in the frame of our joint project. So the scalability is at the level of 80%. 80%. It is good. It is a good value, in fact. Here are some tests for our MPI, CUDA, and OpenMP solvers that was provided by one of our PhD students recently. So, 1 second, please. Yeah, and some more tests. But the goal of my presentation today is to show you how we can use numerical simulation, full wave simulation for different problems. First problem is seismic survey process when we have a day sources like this machine, or maybe some explosion sources, and we have a set of geophones on the day surface, or maybe inside some engineering wells, and due to the interaction of our seismic waves with some heterogeneities inside this geological medium, we can detect a very low, not very intensive movement of the day surface, velocity or acceleration, and we can try to reproduce the subsurface structure of this media. So what we can do, using the forward problem simulation, we can estimate the seismic responses taking into account different multi-phase phenomena of our media, some porous phenomena of our media, some anisotropic inclusions or maybe layers, and fractured media directly. Here I will show you the result of 2D simulation, the triangle mesh. You can see here 10 different layers. So each of these layer has their own density, shear wave speed, and pressure wave speed. And we had we initiated subsurface explosion here, and you can see simulated relay wave here propagated along the day surface, initial P wave, initial shear wave initiated after the interaction with the day surface, and a set of reflected waves. If we will speak about the area of geological massive near to the day surface, we will see that we have numerous layers, sub-horizontal layers, and it is effectively like an isotropic medium vertical transform isotropic model can be applied successfully. So it was done here. I introduced some anisotropic behavior inside the standard Marmouzy 2 model according to this formula, theoretical formula, and I extended our software for the solution of this sort of relogical equations when we have 4 different coefficients rather than 2 for isotropic case. And here you can see in the black color the models of velocity. Because of the curvature of the fractured of the layers, we can see the change of the curvature of the wavefront here, and we can see here a lot of surface waves, and the triangles like here, because at the contact boundary between different geological layers, in fact, we have some specific sort of waves propagated along horizontal axis. One of the interesting thing is how we can explicitly take into account the oil saturation or water saturation of our porous media. There are a lot of different mathematical models like BIOT model and others, but we decided to use our own model provided by the Professor Dorovsky from Novosibirsk. It is the city of Russia, one of very big university, scientific university, is placed at the Novosibirsk. So the system is quite the same as the system of BIOT, but we have the direct contact with the author of the model. That's why it was easier for us to implement the solution of this model. This model is hyperbolic 2 with the right hand. It contains a lot of different parameters to describe the, for example, solid to solid volume to the whole volume of the medium, like porosity. We have to describe the compressibility of our fluid, the compressibility of our skeleton, elastic skeleton. We extended our software, and derived analytically all of necessary matrices, and implemented the solution in the same manner. Here we tested on the simple model. One of the key feature of this approach is that we can explicitly set a physical condition at this interface. Of course, because this is the contact between porous medium and elastic medium, we have to glue skeleton particles from the skeleton here and particles from the elastic medium here. Yeah, so we can set enough conditions for the discontinuity of some set of physical variables, and our method will explicitly fulfill these constraints. Here you can see the propagation of waves. We can see the scattered waves on this contact boundary, the change of the curvature of the wave front, the creation of the second type of the P wave inside porous media. This is the internal property of the Dorovsky and also the Biot model, that they have not 2 velocity speeds but 3 wave velocity. Here I put some description of these wave patterns. One of the other key feature is that we can introduce in our computational mesh, in our grid, we can introduce faults. We can introduce fluid field or fluid saturated fractures explicitly. Here I simulated 3D model that contains vertically or subvertically oriented fluid field fractures, and you can see the creation of the seismic response from this fractured cluster. The interest for this sort of medium is connected with the fact that mostly fractured media is connected with oil deposits. Sometimes most of the oil is contained inside the matrix, not inside the fractures themselves. But in fact, if you want to find huge deposit, you have to track the fracturing of the media. This example provided by our colleagues. We have the real geological data, and we, based on some data from the well, drilled at that deposit, and we constructed the curvilinear model, set appropriate elastic parameters, and simulate the seismic wave propagation. That's this model to compare with obtained data. Here I put the test when we use cubic mesh, and what if we used the curvilinear mesh adopted to the curvature of the geological layer. And of course the benefit must be approximately 30 or 40% if we speak about the amplitudes. And it illustrates that if we want to apply a currently very well promoted method like full wave inversion, we have to use the appropriate direct solver to reproduce correctly, to estimate correctly the amplitude of responses, not only dynamic properties of the time of the signal, like time of arrivals. the power of the numerical simulation is the possibility of simulate some predefined model and to analyze different aspects of responses. Here, I showed the illustration how to split P wave and shear waves inside the seismic response. Here I put the 2D slice of the 3 model simulation here, and here I switched on the visualization of the vector of velocity, and it is clearly seen that this is the shear waves here, and this is the P waves propagated to the day surface. So we can analyze very complex signal when the usage of the traditional 2D synthetic seismograms or maybe area seismograms is not enough to understand the complex structure of the signal. Our software was successfully applied to in the combination of geomechanical simulation when we want to set initially the condition for the creation of fractures, and our colleagues used one of the software provided by Schlumberger and gave us the spatial distribution of the planes of fractures, its orientation, its size, and we started with the synthetic data when we have a set of oriented fractures inside our 3D model. What if we add some changes along one of the direction? What if we add more changes along the second direction and 3D randomly generated medium? And what they do in the field, they try to analyze the anisotropy in the registered seismic signal, and based on this data try to reproduce the orientation of cracks. This is necessary to organize effectively the exploration program on the real deposit. So you can see that if we have one axis of symmetry, we have the anisotropy in our signal. If we add some randomly generated cracks changes in the orientation, we significantly break this anisotropy. And then the real data for one of Russian deposit were used, and the direct solution using the DFN model was done and by our colleagues, and they provided us the model of fracturing of our medium. Here you can see that the model contains a numerous amount, more than 10,000 of cracks with different orientations with the intersection, and this is a simulated anisotropy in this data, and according to our joint analysis, the image is close to the obtained by at the field to the real data. A couple of words about the inverse problems. We can test different inverse solvers. It is very important for real companies because nowadays there are numerous methods and all of a lot of companies want to sell their processing technology, and it is necessary somehow to compare this technology. And in this case, we can provide the direct solution based on some very complex but known model. And in future, the company can use it as a test for different novel technology for the inversion, for migration we'll speak about the seismic survey simulation, seismic global seismicity simulation. It is, I think, more closer to you. So we can use the trivial model of the hypercenter, like moving along the fault, and we solve, in fact, the elastic equation. So our solution is correct in the far away from the hypercenter, but this area is in the most interest, I think, because the area near to the hypercenter is not accessible for scientists or for engineers, but the surface wave indeed break houses and destroy buildings. That's why it is very important to simulate correctly seismic wave propagation from the hypocenter to the day surface, and then its influence on the surface buildings. Here is the comparison of numerical simulated beach ball diagram and analytically constructed by the other approach. Here we used open data to estimate the parameter of the mathematical model, the initial velocity, and also the position of this hypocenter and its spatial sizes. The other approach is a double couple model, very well verified approach when we introduce a set of forces inside our mesh, computational mesh, and the sum of forces is 0, sum of moments is 0. That's why we don't rotate, we don't move our medium, but we put some energy inside the geological massive. And this is the illustration. If we have some plane, some fault, and we have some vector of slip along this force, along this fault, we can calculate the values of these forces applied in our numerical model, and we can reproduce data provided by authors with spectral method. Unfortunately, most of publications don't contain enough information about the source or maybe of some other key parameters of simulation for some reason, and that's why we can't reproduce 100% of the data, but we can simulate this data at least approximately. So, and using modern HPC system, nowadays it is possible to simulate, in fact, earthquake in the whole earthquake model, in the whole Earth model. This is the example. You can see numerous waves propagated along the surface. Here we introduce the mesh inside the sphere, and over the sphere you can see also the special heterogeneity of parameters of this problem. How to use the result of numerical simulation to estimate seismic resistance? We can apply directly these ground motions and track some physical criterion. For example, here we use Mises criteria, and you can see that we can obtain the places of the destruction places here near the window, near the door, and on the roof. But we can follow two different schemes. The first direction is only to track The second is to destroy our model. In this case, it is necessary to use some other numerical method, and we successfully combine our grid characteristic method and SPH particles in cells methods, find the volumetric meshes on the movement meshes. So this direction is very interesting and very promising nowadays. Amit Sharma provided to us the result of the simulation that they done at their laboratory, and we can directly compare the result of laboratory experiments and the result of numerical simulations. I think this direction is very promising nowadays. A couple of words about other possibilities. We can simulate volcanoes. Here is the Mount Elbrus, and one of our colleagues deal with magma movement, and they provided to us quite detailed 2D model of the subsurface area when we have two reservoirs of the magma, and it is necessary to track the situation when this magma start to go up, yeah, to track the dangerous situation, so we can set different parameters inside these regions and start simulation and try to find the information about this fact inside simulated data. Here I will show you what we can do. Sometimes they use active seismic registrations with the source. Sometimes they use passive technologies. Here we use curvilinear meshes. So and I think at the end I will show you a couple of interesting results that obtained my colleagues. This result is not closely connected with seismic survey problem or global seismicity problem, but they are very interesting, I think, because they are connected with the reproduction of experimental data. Here you can see the cubic ice sample, and our colleagues from Ishlinsky Institute applied a load to the boundaries of this cube, and they obtained the crack here. This is natural, but they obtained a ring crack. So it means that inside this material, inside this circle, the material is not destroyed. They have only a ring of the destroyed material, and it was a challenge for us to reproduce this data. We done a lot of simulations, and eventually here with the blue one, with the blue color, you can see this ring reproduced, and this phenomena is connected with the fact that under the load ice can increase the strength, yeah, the parameters of the for example, yield coefficients can increase effectively under the load for ice due to their compactions. If we are speaking about ice sample loading, it is very interesting to simulate complex geometry. Here you can see the LOF problem when we have cone ice. They generated this ice inside some specific device, and they want to apply load to the one boundary of this sample, and under this load they in fact use the mechanical loading for the melting for the initiation of the melting process. Here you can see the result of wave simulation along this sample, and due to the interaction of the initial wave and reflected wave from the other boundary, the melting process started inside the volume of this ice sample. Here I show that some of the verifications that we used when we developed our modules of our software. Like this is the explicit contact with VTI material and isotropic material to test that we can reproduce all of waves for horizontal movement and for vertical movement. Here is a test with the other theory, boundary element method. When we have a thin plate, it is better not to cover the whole volume with mesh because it increases the computational time, but we can solve 2D approximation, and here we have in fact the 3D problem, but simulated in with other approximation. So we have here two rings at the first at the top boundary of the thin plate and at the second boundary of the thin plate, and applying the voltage to these rings, we can, this ring were glued to this plate. We can load effectively this material of the plate. So this plate had an empty crack, fluid, not fluid, but air filled crack, and we compared the simulation carried out with a grid characteristic method, like a full 3D task, and also the result obtained by with our colleagues by boundary element analysis, and it was shown that all of the wave types we can reproduce successfully due to the reasonable time. And one of the interesting problem is connected with the conversion of the P wave to shear waves, because it is quite easy to use specific type of the material to apply voltage and to initialize P wave propagation inside the material. We can use it for ultrasound diagnostic of some materials of our body, but it is quite difficult to initiate shear waves on the boundary of some medium. But we can, our colleagues from China, they carried out the experiment when they created the aluminum plate and they cut this plate in the specific manner, and effectively this plate is the conversion. They convert the P wave to shear wave. The illustration of this process is presented here. We started P wave here, and you can see this P wave in the right part of our domain, and here we have very thin plate with these holes oriented along specific direction. The direction is connected, and the thickness of the plate is derived from the from the frequency of the initial wave to decrease significantly the propagation in this area P wave and convert this energy to the shear wave. So you can see here the initiation of very intensive shear wave after this device. And device this device is very trivial. So any group that has laser cut device can reproduce this this aluminum plate. So it is quite cheap to create this converter. And non-destructing control nowadays is widely used. Here you can see the solution of the contact problem between the rail wheel and the rail wave. The problem of detecting of karst cavities under the railroad, and also the detection of some inclusions inside construct elements of the railways. So thank you for your attention. Here I put my direct emails. So please feel free to contact me if you want to discuss these results or maybe show your results. I will be very happy to communicate with you, all of you. Thank you very much for this chance to present my lecture.
Thank you very much, sir.
I think we have some time for questions if you want.
So one question is there. Is it possible to develop geostatic models to simulate a seismic process?
Geostatic. As far as I understand, there are numerous models, in fact, nowadays to simulate seismic activity, but we have a lot of databases and there are no any models that can successfully reproduce the whole set of data. That's why I think we don't know enough about the physics of the hypercenter nowadays to construct one general model. But we can take into account some different aspect that is very important, like the specific structure of some region, the specific rheological behavior of some soils, for example, some sands or clays. So I think we have a lot of activity in this direction, but nowadays there is no one clear answer to this question.
Sir, one more question is there. Sir, how we can model the ground surface and our structure interaction?
When we model the whole problem, I mean the problem connected with the ground movement and structure behavior, we have to set explicitly some physically correct conditions on the contact boundaries. The trivial one is the glue condition, when we guarantee the discontinuity of the velocity vector and the discontinuity of the stress or force stress tensor along this contact. But when we deal with the destruction, I think we have to take into account some friction phenomena, and we can do it also explicitly. But I think that, of course, we can introduce some damping inside models. We can introduce some nonlinear elements inside our model. But I think that one of the major problem is to provide enough parameters for these models. And I think the laboratory experiments can be used effectively to estimate the friction coefficient, for example. I speak about the real cases, not about some analytical approximation, because in the real life we have different results rather than in our books. So I think we have to rely on the laboratory tests in most cases.
So one similar question is there.
Okay.
How to model soil and concrete interaction in FEM?
soil and model interaction. Where?
A concrete, if there's a concrete structure, RCC structure is there. So how we can model it in FEM, finite element method?
Oh, so if we are speaking about the results that I presented to you, in fact, we are our method is mostly close to the finite volume method when we put the quantities in the volume and provide necessary fluxes to fulfill the energy balance equation, some other balance equations. In FEM, I think we have to add some more contact conditions, maybe. We don't use directly finite element method, but I know that there are a lot of open packages like MFEM that we used recently, shortly. But I think if we are speaking about finite element method, I don't know the appropriate procedure to solve this contact problem.
Sir, I need to ask one more question.
Yeah.
Sir, as we are applying the forces in the form of P wave and shear waves, is it possible to apply in terms of acceleration also?
Yes, in fact, we in our simulation we decided to take into account the whole domain because we can do it in the reasonable time. So we have the hypercenter inside our simulation domain, and we have the ground building in our mesh too. But of course, it is possible if we want to simulate it. I think we have to set the appropriate force on the boundary, and force can be easily recovered from the accelerations. And also, it is very important to provide reasonable damping conditions on the outer boundaries of our domain, and we can use some non-reflecting boundaries conditions or some other modern technique to prevent our waves go back from non-physical boundaries, because we have to cut somehow our model, but in the real life we don't have these boundaries. Yeah, that's why, yes, we can do it. The conversion from the acceleration to the force is trivial, but we have to solve the problem with the artificial boundaries that we have to introduce in our model to prevent backscattering. Okay. Some more questions?
Is there any questions? Or you can mail to sir also if you have any query.
Yes, of course. I hope that we can be in touch. I read my email daily, so feel free to send me any questions or anything.
Sir, they will send to us, or if they send to us, we will revert it to you, sir.
Okay.
So thank you very much, sir,
Thank you very much.
for sharing your time as well as your valuable work with us. And I hope all the participants will try to understand the things, and then they will ask you once again.
Okay, it will be great if you will share the recording, the record of the seminar if you can.
Sure, sir, sure. Sir, some participants are asking for a PPT.
Yeah, I can share with you the presentation, and I think this is open. This is an open material, so don't. It is not a problem, in fact. So, thank you.
Thank you very much.
Thank you so much, sir, for devoting your time and your valuable work to us. We are indeed privileged to have you with us today, and we look forward to having you with us again sometime in future in some training programs. Thank you so much,
very
sir.
much. Thank you very much.
Thank you, sir. And sir, we hope that this collaboration will go a long way.
Yeah.
Thank you.
Thank you very much. So, goodbye.
Bye. Sir. Goodbye. Sir.
Bye.
Now I think this is the end of this